in the last class, we had learned a little bit on IP addressing, then subnetting, CIDR, and then finally we talked about network address translation. Okay. So as I had earlier told also that I will be taking a separate class on IP addressing, and that is today's class. Okay. So today I will just elaborate a little bit more on IP addressing. I hope my screen is visible to all of you. If not, please let me know. Okay. So what do we know about IP? We already know that it is a connectionless, unreliable, and best effort delivery protocol. Okay. So whatever devices are there on the internet, we generally identify them using an IP address. Okay. So whatever data you pass down over the upper layers, at the network layer, what you do is you add the IP address, which will determine that what's the destination address, and also you add the source address in that, so that it's helpful for addressing, for the purpose of addressing and delivering the packets. And then correspondingly, the packets are delivered from the source to the destination using IP address. Okay. And as we have already seen, that every interface of a host is given a IP address. Okay. So you had seen that in the last class when we were looking at subnets, each router's interface was given a IP address. Okay. Because you, if you are having different interfaces, you can have communications on them parallelly. So in that case, you can actually use different IP addresses to identify the different interfaces that the host is currently having. Okay. So this is how your network address basically looks. Not network address, sorry. In When you are transferring data from one host to another host, with each router, you see that um, suppose X is the source here and Y is the destination. So it's given out that the packet from X actually moves through all the, so here we can see that it is a 7-layer application. Okay. Sorry. So you have 7 layers here, not the 5 layers that we have talked about. Okay. So this is called a OSI layer representation. Okay. That has 7 layers. In our TCP IP that we have studied, these 2 layers are not there. That is presentation and session layer. So presentation and session layer basically consists of applications like synchronization, error control, etc. So uh, those applications are already added in the application layer of our TCP IP. We have already studied that in the first classes. So this is just a 7-layer OSI representation. So if it's your TCP IP that we have already studied, then these 3 application, presentation, and session layer, those will be combined into one, that is application layer. Okay. So in that case, we will have our 5 layers in that case. So here what's happening, the packet that is being transmitted, that will be transferred over the layers through the physical medium, and then it will reach a particular router. We all know that at the routers we have up to the network layer, because it does not need to do any further decapsulation. There's no need for any other kind of demultiplexing at the routers. They are only concerned about, or they are only concerned with how to send the packet from the source to the destination, and what is the next port through which the particular packet has to be transferred. So that is why only up to network layer is concerned. So it is moving through different routers, and therefore at different routers you can see that these are the layers, and the packet actually moves as per the arrow that has been given here, through A, then B, and then goes through C. So this is given here like that. From C, the path goes to the destination, which is Y, and then at Y we know that it goes through all the decapsulation or demultiplexing methods. Okay, up to the application layer. Okay, Let's get to IP address. So what we know until now is that we are looking currently at Ipv4 addressing. So we have 32-bit IP address here. Okay, and in this 32 bits we have the network part and also the host part. Okay, the network part will determine that what's the subnet and some other things also, which we will look at here in this class. And the host part is basically going to tell you that what is the host's actual host's address. Okay, so this variation will give the different addresses to different hosts, and this variation at the network side will give the addresses of the subnet parts. Okay, so here we are not looking at the subnet part as of now in this part. Okay, we will call it as the network part and then we'll call the host part. Excuse me. So if it's all in binary, the entire 32 bits, we know that it will be very difficult for the users to actually um, use it. Okay, so to increase the usability and to increase the understandability of IP addresses more by the customers or by the users, the dotted decimal notation was proposed. Okay, so what is the dotted decimal notation? That's how we generally know the IP addresses as. Okay, we know them as like this: 172.16.122.204. Okay, so what is done? We have a 32 bits address and we divide it into parts of 4, each part having 8 bits. Okay, so that represents a particular decimal number and they are separated by dots. So that is why it is known as a dotted decimal notation. All right. So yes, this is the Ipv4 addressing that we are looking at. So it is said that the Ipv4 addresses are unique and they are universal. Okay, that means all the nodes connecting the internet must have IP addresses. All right, and the address space for IPv4 would be 2 part 32 because we have a 32-bit address, right? Now we will see that with this kind of requirement and with this kind of availability of addresses, what are the challenges that we are going to face with IPv4? Okay, but before that, what we need to see is that how is this entire chunk of 2 part 32 bits address, or sorry, 2 part 32 address space is actually divided amongst different hosts throughout the world, right? So we need to address them. We need to give special or some chunks of addresses to different organizations, and then we need to identify that which organization gets which IP, right? So there are two categories or two ways of addressing these hosts. Okay, one is known as classful addressing, and another is known as classless addressing. We have already read the classless addressing part in the previous classes. Today I am going to teach you the classful addressing part. Okay, it is a previously used addressing technique. Nowadays we use only classless addressing, but in classful addressing, we need to understand that how the division used to happen and why we went to the classless addressing. Okay, so that is why I'm teaching this part also. So classful addressing, what we used to do is that the entire address space was divided into some subclasses or classes. Each class was named as A, B, C, D, and E. Okay. Now, as I told you that this is not used anymore now. Why? Because a large part of the available addresses were getting wasted in this case. And now we are going to see why. So first, let us see how this division of addresses used to happen. Okay. So the class A address, as you can see here, okay, class A address. what happened in this case is that we know that we are basically dividing in IP addressing that chunks of 8 bits together, right? So that means first byte, second byte, third byte, and fourth byte. All right. So if you consider these in binary format, the first one starting with 0, just the higher order first bit, so that came under class A. Okay. Then class B, if the first two are 1 and 0, first two bits, then it came under class B. And class C, if the first three bits were 110, then it came under class C. For class D, 1110, and for class E, all four ones. Okay. So this is how the classes were divided. Okay. Now, correspondingly, if we have first bit as 0 here, so in dotted decimal notation correspondingly, all the IP addresses that started from 0 to 127 in dotted decimal notation, all the addresses that started from 0 to 127 that fell into the category of class A addresses. Now similarly, if you consider the first two bits as 1 and 0, then from 128 to 191, the first byte, if it was the first notation number, if it came between or if it was under 128 to 191, then it fell under the class B. From 192 to 223 fell under class C, and from 224 to 239 was under class D, and from 240 to 255 was under class E. Okay. Now you can ask me the question that why are these yellow parts here? Okay. So if you remember, we have a network part and we have a host part. Okay. So the yellow parts, they are basically defining that what could be the host part and what could be the network part. These yellow parts are basically defining the network part here. All right, like this. So class A, see here, if you see that we have total 8 bits, right? So the corresponding decimal notations will come like this. So that is why if you go to the previous slide, class A addresses start from 0 to 127 as the first byte here. So the network part is, so 0 is the first bit here, and the rest of the 7 bits will define what will be the network part. Okay, so all the variations in so you have 2 power 7 variations, right? So that much of network part you can have. Okay, that many network addresses. The rest of the 24 bits, they will define what can be the host addresses. Okay, there will be different host addresses accordingly. Okay. Now, correspondingly, class B addresses. Okay. First two bits are representing the class, right? That is 1 and 0. Now, the rest of the 14 bits will define the network part. Okay. And the rest of the 16 bits will define the host part. Like here. See, the first two bytes are defining the network part, and then the rest two of the bytes are defining the host part. Out of the first two bytes, 1 and 0 from the first byte, that will define what is the class. So that is class B addressing. Class C, first three bits are 110, and rest of the 21 bits, they define the network part. Okay, and then rest of the 8 bits will define what's the host part. All right. Now, class D, what do we know? In class D addresses, there's nothing like this. We are simply saying that if it is starting with 1110, the in the first byte, the first 4 bits, if they are starting with 1110, then it falls in the class D address, and class E, if the first 4 bits are 1, then we call it as it falls under class E. Now these are some special classes. Okay, we'll see what they do. The class D addresses are generally used for multicasting. Okay, that means you are trying to send your data to different destinations at the same time. So in those cases, you keep these or you use these addresses, and they are called, the application that is used for is multicast. The last category is a reserved category of IP addresses, that is category class E addresses, and all the three others, that is class A, B, and C. See, they have these many number of address blocks. Okay, 128, because you know that you have only 7 bits of network address there. This is according to the number of network address that you can have. This is 16,384, and this is 2097152. So much larger number of network blocks. I mean blocks, which will be basically the network parts. And this is the block size. Okay, and these are used for unicasting, that is one to one, source to destination communication. All right. So this is just a explanation of what I just told, that your class A addresses will begin with 0, first bit as 0, and then you have rest of the 7 bits as the network part, making the total 8 bits of the first byte. So the total 8 bits will basically form the network part, and rest of the 24 bits will form the host part. For class B, your addresses will begin with 1 and 0, and the 16-bit, you have 16-bit network part and 16-bit host part. For class C, your address will begin with 110, and you have a 24-bit network part and 8-bit host part. For class D, your address will begin with 1110. It is a multicast address. And in class E, which is in general not used, that begins with 4 ones. Okay, and then the rest of the part it is given as 0 here. 4 ones is what class E starts with. Now, because see, with this kind of categorization, you are basically getting limited with how many number of addresses you can have, and also some of the addresses are basically not used here. Okay, so instead of using this kind of addressing scheme, a new addressing scheme was proposed, and that was called as this classless interdomain routing. So there's no class as such. Okay, so IP addresses are there, the entire address space. Somehow you get to know that what is the subnet part and what is the host part. We have already studied that how we get to know what's the subnet part and what's the host part in our last class. Okay, we know that the subnet address is given by the ISP, right, and the host gets the corresponding address from the rest of the subnet. I mean, after the subnet part, whatever the rest of the bits are there, from there we get the host part, right? So the subnet gets its address from the ISP, and the ISP further gets the entire block of IP addresses from ICANN. Right, that's what we have already studied. So CIDR or classless interdomain routing is the way of addressing IP addresses or categorizing IP addresses, where we know that the network part that we were calling in the previous slides of the IP address, that we call it as the subnet part, that defines as to what are the different basically what is the subnet part of this, and the host part will define that what are the different hosts associated. Okay, and in dotted decimal notation we know that this is the IP address, and the rest of the part, that is /23 here, that is defined as the subnet part, which will basically define that how many bits are actually acting as the subnet part. Okay. Hmm. Okay, now some useful information has been given here. Okay, so we already know by now is that um, we are insider, we are defining a block of address as a dot b dot c dot d slash x, and your a dot b dot c dot d is basically your address, and the slash x is basically defining your subnet mask. That means how many bits are actually representing the subnet part. Okay, now in this entire set where you say that a dot b dot c dot d slash x, these are a block of addresses, right? In this, what should be the first address? Okay, the first address of this block can be found by setting the rightmost 32 minus x bits to zeros. So let me give you an example. Here we have 200.23.16.0 slash 23. Okay, so this is actually the first address. Why? Because 32 minus x if you do, okay, that means x is 23 here. That many bits, if you set to 0, then that becomes the first address of this entire chunk of addresses. Okay, so here this 200.23.16.0, that is acting as the first address. Okay, and then what should be the last address? All these host parts, the bits which are there in the host part, there if you put them as ones, then they become the last address of the given block. Okay, and how many number of addresses can you put in this particular block? Of course, that will be 2 power 32 minus your x. It is given n here, that is incorrect. Okay, it should be x here. Okay, now the first address is normally not assigned to any device, because it is basically representing your subnet. Okay, so it is used as the network address that represents your organization. Okay, so if you are basically part of an organization, the first address, which is having the host part as 000, those or that address will basically define the address of your organization to the world. Okay, so that is why it is generally not used. All right. Now, each address in a block is considered as a two-level hierarchical structure here. The leftmost n bits define the networks, and of course, we know that the rightmost n bits, they define, rightmost 32 minus n bits, they define the host part. Okay, and the number of subnet bits, they represent the subnet mask. Now, let's see how to do the subnetting. Okay, so here we have an IP address 223.1.17.0/24. So since it is .0, we will know, or we can guess here that that is representing the organization's IP address, or the first address of this block. Okay. So how many IP addresses can it have? It can have 2 power 32 minus the number of bits in the subnet part. So that's given here. Okay. Now in this, if you want that, what can be the further variations that you can have in this entire organization's addresses, a chunk of addresses. So you have 256 addresses that you can have, right? So subnet 1, we are saying that, okay, we will divide the given 256 addresses into different blocks further. So this is the first block of addresses. Okay, so you are taking or making a difference in the 6 bits. Okay, so that is some 64 addresses you can have, which are having a difference. So then your subnet part becomes what? 223.1.17.0/26. So this is your first address, and your last address will be 63, turning all of them as ones, right? Similarly, for subnet 2, you again are dividing it into 64 different addresses. Okay. So then next your starting will be from this part. Okay, this is a continuous chunk, right? So 223.1.17.64, and this is your subnet mask 26, and the last address will be this one, that is 223.1.17.127, turning all of them as ones. Okay. Now the rest of the subnet, you are saying that okay fine, we will have just three divisions. So the last one will have 128-bit addresses, considering that you have a total of 256. Okay, so then you can represent it as 223.1.17.128/25. Okay. Now what we have studied in the class, last class, we had studied a little bit on NAT, okay, network address translation. So what we had studied is that you can have an organization where you can have different hosts which can locally be given some IP addresses and which is not known to the outside world. The outside world knows your institute with a single IP address or your organization with a single IP address, and it is the job of the network address translation router or NAT router to actually do all of these conversions. Okay, so to the world, the organization is known by this particular IP address, that is 200.24.5.8, but inside this interface to the NAT router is known as 172.18.3.30, and each of these hosts which are connected to this router, those are given different IP addresses locally. Now, if there is some data that needs to be transferred from either the host to the outside world, or it has to come back from the outside world to the host, the NAT router is the one that converts or does the conversion between the given IP address from which it is arriving to this one, that is the interface of the outside to the outside world, and vice versa. So this is what we were doing. So if this is the source which is sending a packet, so in the header you will have the source address as this 172.18.3.1. In the NAT router, there will be a NAT translation table there where you will put up this information that this host is trying to send an information to the outside world. The source address is 172.18.3.1. Okay, and for any particular destination address it is sending, that will also be put up in the NAT table. Now in when the packet is being moved from the NAT router to the outside world, in that case this 172.18.3.1, this is replaced with the interfaces address, outside interfaces address, which is 200.24.5.8. Okay, so this is how the transmission of the packet happens from the organization's host to the internet. Now, similarly, when there is a reception from outside, so the destination address will be simply the NAT router's outside address, outside interfaces address, that interface that connects it to the internet. Once this packet comes to, or any packet comes to the NAT router, with the help of the NAT translation table, the destination is converted to the correct host's destination address, that is 172.18.3.1. So after this translation only, it goes to the correct host. Alright, so this is how we had seen in the last class also. I'll not repeat this again, but what we will do is that what are the advantages that NAT actually gives us. Okay, so one of the advantages, as we had already seen, is that your entire network is actually defined by just one IP address. Okay, to the outside world, the only IP address that is required is your organization's IP address. That means the interfaces address, which is basically connecting to the outside internet or outside world. Whatever is happening inside your organization or whatever IP addresses you are using inside your organization, that is not of concern to anybody outside the world. Outside your world. Okay. So what happens in this case? For the ISP, when it is actually going to give the chunk of addresses, okay, it is not needed for anybody to basically send the range of addresses to the particular organization. Only one IP address is going to be okay, because the rest of the addresses inside your host, those are those are local. So those can be anything that your organization wants you to give. But outside, for the outside world, the ISP will give just one IP address for all the devices which are associated to your organization. So this basically helps to reduce that problem. Which one? IPv4 addresses are less given the millions and millions of devices that we are having in the world, right? So if for an entire organization, if only one IP address is sufficient, so then this reduces the problem a lot, right? Now, what is the other advantage that it gives? That with the help of NAT, you can change the addresses of devices in your local network without the outside world knowing anything. Okay, you can change the ISPs, you can change even the IP addresses inside. Whatever you want to do inside, you can do in your local network. But because the outside world is not knowing any of it at all, the outside world will simply um, define or the outside world, for the outside world, your organization will simply be defining the IP address that has been assigned by the ISP. Okay. Now, another thing that is a very big advantage when we use NAT is security. Okay. So, since the devices which are there inside the organization, inside the or devices which are locally present inside an organization, they are not explicitly addressable by the outside world. So that helps in security a lot. Okay. So these are the advantages that we get if we use network address translation. Okay. Now, if we have to implement NAT, then what are the things that we must do, or things which are like most important when we are trying to use NAT? Okay. So, first is that all the outgoing datagrams from your organization, their address must be replaced, the source address, right? Because the outside world, of course, does not know about the local addresses given inside the organization. So all the datagrams that are going out, their source address must be replaced with the NAT router's outer interface, right? Now, the next one is that, again, the entire load comes to the NAT router, because it also must have the NAT translation table that will have to remember that which organization was sending, which host in the organization was sending the datagram, and it has been translated to, and if there is a um, corresponding datagram that is received from the outside world, uh, then which particular local excuse me, which particular local host in the organization has to be forwarded this particular data. So it all comes upon the NAT translation table, having all this information about different hosts in the organization, what are the datagram exchanges that are happening with the outside world. Okay. And similarly, whenever there is a datagram that is received, there has to be a replacement to the correct destination address, right? So these are the tasks that are to be carried out by a NAT router, making the NAT router the most significant actually, the most significant part of this NAT translation, and also the most complex part, right? Because it has to do the maximum tasks. So this example I had given in the last class also, but it was in a hurry. So I will again just go through it very quickly. So suppose this is a host, this is from the organization side, this is local to the organization, having an IP address of 10.0.0.1. Okay, so this sends a datagram to the outside world, some other host having the IP address of 128.119.40.186, port number 80. Okay, now this is the local interface of the NAT router 10.0.0.4. Okay, and we have a NAT translation table here. So what happens when this datagram reaches the NAT router? First, the NAT translation table has to remember, right? If you remember, it has to remember what's happening, and it also has to, and the NAT router also has to replace the source address, right? So that's what is happening here. The source address is changed to the outside interfaces address, right? That is 10.0.0.1 is changed to 138.76.29.7, and the corresponding port number is 5001. And the corresponding translation table also is given here. Just hold on a second. Hello, am I audible? Hello?
Yes, ma'am.
Okay, okay. So in the NAT translation table, we have put this particular address, that is 138.76.29.7. That is the WAN part, that is wide area network side address. And the corresponding LAN side address is 10.0.0.1 with port number 3345. Okay. Now, when there is a return of a packet or a reply of the packet that was sent earlier, so then the address of the source is of course 128.119.40, all right, 40.126, 186, sorry, with port number 80. And the destination address will of course be the outside interfaces address. So that is 138.76.29.7. And correspondingly, when it comes to the NAT router, what will happen? The destination address has to be changed, and it is changed with the information that is already remembered by the NAT translation table while the packet was being transferred, right? So the NAT router will change the datagram destination address from 138.76.29.7 to 10.0.0.1, and port number is 3345, and correspondingly it will be sent to the corresponding destination address. So this is how the NAT translation happens. All right. Now, if you remember, when I was talking in, yeah, I think one class before this, yeah. So before one class before this, I was talking about what are the modules that we have to study in the network layer part. Okay. So one thing we had studied about, how the what is physically inside a router, what is the control part, what is the data part. Then we came into IP addressing that we have already studied by now. And then we had a part called ICMP. Okay, we still have to do the routing part that is left, but we are currently at the ICMP part. Okay, so what is ICMP? ICMP is Internet Control Message Protocol. It is basically used by hosts and routers to communicate some network level information with other hosts. Okay, and what are these network level information? Like, if there is some error, okay, in the path, okay, while transmission, if there is some error, like, there is some link got disconnected, or there is too much congestion in a particular link. Okay, so these are some of the incidents that need to be reported to other hosts. Okay, so in that case, that comes under error reporting. So if the host is unreachable, or the network port is unreachable, or a given protocol has changed, so those are the issues that need to be communicated to different hosts. Okay, and the other one is echo request or reply. So if all of you might be knowing the ping command by now. So that is part of the ICMP. That is basically going to tell you that whether your data that you are basically sending, that is actually going to reach the or is reaching the host or not, and the host is able to reply to you or not. That's what the ping command tells you. It is basically coming under the ICMP protocol. Okay. So the ICMP messages are basically carried in the IP datagrams. Okay, so what does an ICMP message consist of? It consists of the ICMP type, which is basically a number that defines what is the type of message that is being transferred. Okay, and there is a corresponding code related to that. Okay, and then you have the first 8 bytes of the IP datagram that will basically say that what's causing the error. So if you see the first, so let's see the type and code. So this is a pair, right? Type and code pair. So if they are both 00, then that means it's an echo message or a ping message. If the type is 3 and the code is 0, then the error message is basically the destination network is unreachable. Okay. So similarly, you will have all of these different kinds of type and code pairs, which will say that what are the different types of errors, or which will basically represent the different errors that can be communicated with the help of ICMP messages. Okay. Now, until now, we have studied about IPv4 addresses. Okay, so we have studied how many bits IPv4 addresses has, that is 32-bit addresses. Then we have divided them into different types of addressing, that is how the IP addresses can be defined. So classful addresses and CIDR. And then we have studied the different ways of representation, that is using subnet part and network part in case of CIDR, and in case of classful addressing we had simply the bits representing what class it belongs to, the network part and the host part. Okay, this is how the IP addresses were defined. IPv4 addresses are represented with this dotted decimal notation. Now what we know is that it is having only 32 bits. Okay, so the address space is 2 power 32. Now even if with NAT you can say that with NAT only one address is required per organization, because you can have so many other hosts within the organization which can get some local IP addresses. But still the number of organizations that are there with the entire world's population, as you can see, that is going to be quite high, right? So it is very much possible, or it is actually going to happen that the 32-bit address space is actually uh, finished, okay, or it's all taken over. So in that case, the number of devices in the world, or number of organizations which can be given these IP addresses, that is going to increase only. That is never going to reduce. So for that reason, IPv6 came into picture. Okay, it is a different way of assigning IP addresses to different devices. Okay, so what is the difference between IPv4 and IPv6? We have a larger address space in case of IPv6. And what's that address space? So instead of having only 32 bits, in case of IPv6, we have 128 bits. Okay, so we represent the IP addresses as 128-bit IP address instead of 32 bits, making the address space as 2 power 128. Right, so that is a very large address space. Okay, so apart from this, very large address space, what are the advantages that IPv6 basically gives? The header format helps faster processing of forwarding. We will see what is the difference in the header part of IPv6 and IPv4. And also, because of this change that is made in the header, it facilitates better quality of service or QoS. Of course, the header processing, if the time reduces, then the entire processing delay that will also keep reducing at each of the uh, intermediate nodes, right? Leading to lower delay or better QoS. Now, what is the datagram format for IPv6? You have a fixed 40-byte header, and there is no fragmentation in this case in IPv6. Okay, so given these properties, let us see how does the IPv6 datagram format looks like. Okay, so sorry. So first is the version. Of course, will define IPv6 the version. Next is the priority field, which defines the priority among the datagrams in the flow. Okay. There's another point, which is the flow label, which identifies the datagram in the same flow. Okay. Now, the concept of flow is basically here it is written that it is not well defined, but it is basically nothing but, how do you identify the datagrams which are acting or being transmitted together in the same flow. Okay. Now, then comes the next header, that is which defines what is the upper layer protocol for the data. Okay, that's this field, that is next header. Rest of them you can already understand, and you already know payload length. What is the length of the payload that you are sending? What is the hop limit, that is max hop limit that your packet can or your datagram can actually incur? Then you have the source address, the destination address, and the rest of the payload data that you are sending. Okay, so this is your IPv6 datagram format. Now, what are the other changes that we have apart from these header changes in IPv6? One is checksum. Checksum is not there in case of IPv6. In order to reduce the processing, we do not have the checksum part. Okay. Then the options part is also not there. If you remember, in IPv4 header, we have the options part. Okay, but that is basically replaced by this next header field. Okay, so we do have an options part, but it is outside of the header and it is indicated by the next header field. Okay, then it is not exactly outside of the header. Okay, it is, see, it is here only, the next header part. Okay. Then what we have is the Icmp V6. All right, so Icmp V6 is the new version of Icmp here. All right, so you have some additional message types, like, if the packets are too big, then that kind of message can be transmitted. Because why do we need this one? Because here we are not allowing fragmentation, if you see. Okay, and then you have some multicast group management functions also, which are additional ones in case of Icmp V6. Now let us look at the differences between IPv4 header and IPv6 header. Okay, we've already seen just now that what is the how does the IPv6 header looks like. We have the version, we have the priority or the traffic class, then we have the flow label, the payload length, next header field, hop limit, source address, destination address, and then we have the data field. Whereas in IPv4, see how many different fields are there here. Okay, so how much of header length is there in IPv4? 20 bytes plus options. And then in IPv6, it's 40 bytes plus extension header if at all. So what are the different address types that IPv6 basically allows? Okay, so first is of course unicast. Okay, and where your address is there for a single interface. You can give multicast addresses. You can, which is nothing but one to many. Then it also enables more efficient use of the networks and uses a larger address range. Of course, it has 128 bits, so it uses a large address range. And the other kind of address type is anycast address. Okay, so what is the anycast address? So these are the following ways of anycast. That means one to nearest. That means you sending from the host to the nearest interface. Okay, this is allocated from the unicast address space itself. Then multiple devices can share the same address. That also falls under anycast. All anycast nodes should provide uniform service. Okay, of course, if you are doing this kind of a transmission where you are sending data from one to the nearest and multiple devices are sharing the same address space, then it is always easier to provide a uniform service in such scenarios. Then you have the source devices send packets to anycast address. Routers decide on closest device to reach the destination, and this kind of anycast addresses is suitable for load balancing and content delivery services. Okay, where you have to deliver a particular content to many addresses, and if they can share the same address, then of course it becomes easier to do this content delivery services. So we do have something else also to add, that is IPv6 address scope, where we will see about the different types of address scopes here, that is link local, unique local, global, and what are these kinds of addresses and what is this address scope actually mean. So that is what we are going to do in the next class. But just the last thing that I want to teach right now is that IPv6 addresses are represented by 16-bit hexadecimal fields. Okay, so this is how an IPv6 address is basically represented. So each of these X is a 16-bit hexadecimal field, and you have a total of 128 bits of address. Okay, all right. So I am stopping the class now. If you have any questions, you can